Alright, time for another DraftPhysics.com video presentation. So this is a response video to a physicist Michael video titled Testing the Motion Sensors. Now it seems pretty clear he's made this video in response to my challenge that his detection method for velocities of these carts is flawed. That it's not capturing a correct number because of the fact that he's creating free momentum, in my opinion. Well, frankly, it just as a fact is from Newton's perspective. So this goes to the vector scalar mush that where physicist says that momentum can cancel, that there's such a thing as a negative momentum. Now, back in Newton's and Descartes' day, they did smash things into each other like clay. And they figured out that, yeah, it stops moving, but what they figured out is the clay is still moving. So the motion didn't cancel in any way. It just got converted into what you could call heat or liquefaction, or there was lots of movement continuing. All of that movement ended in some sort of friction and ultimately in some sort of heat. So it all dissipated as little things moving rather than either one of the big things moving. So they already kind of figured this out in Descartes' day. So we're talking 1630. Maybe even Galileo, speculated on the subject. And what physics is saying now is that somehow the energy actually does just cancel. It just cancels. There's no two things can fly into each other and make them stick and the energy cancels. There's no more momentum. It's dead. It's gone. It's disappeared from the universe. That's what they're sort of saying. Okay. Now you can find this out, like you can take two steel balls and you can bang them into each other like a Newton's cradle. Okay. You can bang them into each other and force them not to move. And the fact is they'll get really hot. They'll burn a piece of paper. You can put a piece of paper between them and you can burn the paper, because all of the motion has to be converted into something. It just keeps vibrating back and forth, and it actually burns rings into the paper. So you can actually see the energy going back and forth because it actually creates rings. So those experiments are out there. I just say you don't have to take my word for it. You can go research it yourself. But that's the phenomenon pretty much. But if I allow a Newton's cradle to happen and they just click, yes, there's a little bit of friction, they make a little bit of heat, but the energy is conserved in the motion. So if I prevent the motion, something has to absorb it. So if I prevent them from banging off of each other, Velcro or some other mechanism, that Velcro is going to go through a lot of machinations. It's going to be doing a lot of work. A lot of stuff is going to be moving because the energy is real. The motion is real. There's no canceling. There's no such thing as unmomentum. So that's the basic principle. So this all goes to a particular experiment that I say isn't real. That is, people can do it, okay, but it's not real. What they say is happening ain't happening, because it's a free energy experiment, frankly. Free momentum is free energy. So the idea is you have a one mass cart, you bang it into a two mass cart. Now it could be a 3 or it could be a 5. And so I'll just demonstrate it. They always do it this way for some reason. And there's a spring between them. And the two mass cart leaves with this relationship. So Newton would say these are the numbers. You bang 1 into 1, all the energy goes this way in the Newton's cradle. You bang a 1 into a 2, 70% goes this way, 30% goes that way. So that's this experiment here. Bang it into a 3, it's 50-50. Bang into a 4, it's 30-70. It goes the other way. And ultimately, when this thing doesn't move, you get 100% back as a reflection. You can't get a reflection if this thing moves. The more this side moves, the less this side's getting a reflection. Simple fact. And these are their numbers. So they say these are the real momentum numbers. Okay, so they say when the 100 goes in this way, okay, everything's just 100 in this way, 100, 100 in. And these are the out numbers I'm showing here. You can put 100 in this way, you get 200 this way, and you get 100 back this way, for a total of 300, frankly. And you start with 100, so you got 200 free momentums. That's what they say actually physically happens. Now, we'll get back to this experiment. So you hit when you have 100 momentums going in, you end up with 133 going this way, and you get 33 back this way, for a total of 166. So you got 60% free momentum. But they could do the experiment where it's 50, 150. Or they could do the experiment where it's actually 199, 99 back. And that's the one that really makes a mess out of it. Because I could, theoretically, have a spaceship, let's just say again. I like doing spaceship examples. And I could stay in gravity, so there's Earth's gravity. I'm flying against the gravity, so the pendulum still works just fine. And so I swing a pendulum with 100 momentums into the side of the ship. So all I'm doing is 100 in. Well, let's say, 100 in. And I hit the side of the ship. They're stating that 200 goes into the ship. Now, we could say 199, and 99 back. But, they say the 200 is there. They say twice the momentum is actually in the object. And so what happens is every time the pendulum hits, it moves the ship this way. Right? Can't help but do it. So it turns the ship. And then it bounces back with 99, like I'll get most of it back. And then it hits again. And I get another 2. And then it hits again and again and again. Yes, it will degrade because of friction and other air resistance. I could take the air out of the ship, that's no problem. So it can do this numerous times, maybe 50 times. The pendulum can swing up and hit. And, it's going to start at 200 momentums into the side of the ship. And yes, it might end with 20. It gets very weak as it runs out. But you could figure that there'll be 2,000 or 3,000. So 2,000 or 3,000 momentums will hit this side of the ship. And the ship will have to absorb them this way. It's this, imagine this at the tip of the ship. So it's going to turn the ship. It's going to turn it because I'm hitting it, causing energy to go into the metal of the ship. The whole ship, this side will both move this way because I'm hitting it with real force. There's 2 momentums going that way, 200, twice the momentum going that way. I'm just saying, so that doesn't make any sense, right? This can't possibly be true, but that's what their theory overtly states. It's true. So I can do it with a Newton's cradle. I could theoretically, like I said, why do they always pick this experiment? Why don't they pick the 99, 199 goes this way. If I make this like a 4.7 mass, I get 199 going this way, and then 99 back. So why don't they choose that experiment, since that's so much more dramatic? So go ahead and do that. Let me see you do it, and let me see you do it with a Newton's cradle. Let me see you actually perform this experiment where you crash the little thing in. You create your 200 momentums going this way. You have 100 going back up this way. They're both in gravity, so they're coming back down again. You have 200 is going to crash into 100. Now, all of physics says, all of Newton's physics says, when that event happens, there's 300 momentums there. And what happens in reality? No, just the 1 goes back at 100 again. So all I get back is the 100. So the experiment really does prove it. Newton's cradle doesn't do any of this magical stuff. You don't get any of this free energy. So that's my argument. It's a theoretical objection. I'm not saying you can do experiments and you can verify your velocimeters, okay? All you want, your ultrasonic mechanisms that have to hit a pretty big piece of surface, apparently. But anyway, I can't detail what's wrong. I don't really want to. Maybe I can. How you're getting buggy numbers. But I'm just saying, if you're creating these numbers okay, I think you're out of luck doing real physics, because real physics doesn't have free energy in it, and this is free energy. Free momentum is free energy. Momentum does not cancel. There's no such thing as being a vector. Being a vector doesn't mean, being a vector means you're going in a direction. It doesn't mean you have negative momentum, that you can have such a thing as unmomentum. You can't. All movement is real in the universe. If you start with 100 in, that's all you can have in the experiment at any one time is 100. You cannot have this stuff over here. You can't do it. It's not physically possible. And experiments where you take off these springs and do the experiment, do different things to see if you can find this experiment is consistent. And most importantly, do this 99 to 199 experiment. Do the really heavy mass that barely moves, that's supposed to have 199 free momentums. Do that one and do it in a Newton's cradle, okay, and see if it stays in the system. See if your 300 momentums is real. Because if only one comes back with 100, it's clearly not real. And that's what really happens. So I've shown that in a clip, the Newton's cradle, and clearly when all the energy is put back into the one object, so they swing apart, they crash, energy goes both ways, then they crash again, and all the energy just goes into the light object again, and all that comes back is what you started with, 100. So if you had 300, you have to have an explanation that it all disappeared, and that when they crash into, when the one crashes back into it, it's going to recreate the kinetic energy. I don't think so. It's not possible. It's not theoretically rational or reasonable, and so you have to explain these paradoxical implications of your theory if you're going to defend your experiment, because it's legitimate to have a theoretical objection. I don't have to find the specific flaw in your experiment. All I have to do is point out how it creates a fact that is paradoxical, that doesn't fit, that is in contradiction with other known facts. And the biggest known fact here is there is no free energy. If it was that simple, we'd all have one. I think that's enough of a video. I'll think about it and then decide if it's enough. Since I'm here, I might as well illustrate. I've made this argument in a previous video, and it's unfortunate I don't get any replies to those arguments, so I end up repeating the argument. So I'm going to repeat this one because it's a good argument. Now, I theoretically could make a device that takes advantage of this free energy. And so we just set up this Newton's cradle idea where I just have a mass, and I'm going to swing it into the surface. I'm going to get my 99 reflection back, my 99% of my energy back, and it's just going to go back into gravity and come right back down again. And all I have to do is keep switching out the mass here. So I take this mass, the 4 mass, whatever the right number is to get my 199, and I'll get my 199. I just have this rotate, 4 masses. I just pop a new, every time it goes back, I just pop a new 4 mass in. So I shoot this one off at 199, and then I pop this one in, and then it shoots off because I'm going to lose a little bit. Let's say it's 195, and then I rotate that third one in, and that one's going to be 187, and I'm just going to collect all of this, and when it totals out, I'm going to end up with 2000. So I put 100 momentum, I put the energy of 100 momentum into the experiment. So that's all I did, 100 in, and I get 2000 out. Now, we know there's no way you could do this. So if I did this on the spaceship, it was even a clearer example, right? Because if I shoot a mass out of my ship at a velocity, we know I'm going to be going the other way. So from the equal and opposite, because it took work to do that. So I'm going to end up minusing in the other direction. So this would all be turning power. So with 100 momentums, 100 bits of energy in, I'm going to get 2,000 bits of energy out. Come on. It can't be true. And I don't see any way you evade that that's what your theory implicates. It says that happens. It says I can build this device. So, frankly, I know it's not worth trying to build because I know it's not going to work. Because your theory, okay, your argument that your experiment has proven is flawed because there's something wrong with the experiment because it's showing something that can't be real. And it should be enough. Yeah. I'll declare it. Well, maybe. Let me go back and look. Alright, so on the debatephysics.com website, I do have 10 of these arguments, and 2 of them are fairly related to this idea. So one of them's titled, yeah, whatever it's titled, in space. Maybe that's one of them actually connected to it. And then the negative momentum one. So number 9 and number 6. But there's also, yeah, certainly number 9. That's the one showing the Newton's cradle. And so, you know, the weird part is that, you know, to me, it's not even a kinetic energy argument. This is a, you know, they keep processing their mathematics, that is, you know, comparing things that aren't necessarily the same thing. And so they end up doing these derivatives of the mathematical formulas and create something that says this happens, and then they verify it happening, you know, in some halfway, banging the 1 mass into the 2 mass rather than banging the 1 mass into the 4 mass and getting the much higher yield of free momentum, are frankly showing us the Earth moving every time the pendulum hits a brick wall, you know, and bounces back. You know, on an anvil, for example, I could put the steel ball and an anvil on the other side, and I could just have the steel ball bounce off and just keep bouncing and bouncing and bouncing and bouncing. And the argument would be every time it hits, it makes the Earth move, you know, with 2 momentums. Again, trolling up thousands of momentums going into the Earth. And I only needed the energy of, you know, 100 momentum to create thousands of momentums out. It's an engine of sorts, and it just can't be denied that it could be capitalized on if it was real. If it was real, we could steal this energy. This would be a place to go get it. Alright. Shouldn't have to say this much further. I'm taking, you know... Yeah. Anyway, I think I've made the point, so I'll leave it there. So till the next time, and such, and so forth and whatnot. I think it's enough. Yeah.